First of all, tutorial start this week. Some of you may have already attended your first tutorial. Webcast should be okay now, right? Okay. I try to maintain both IVLE and Luminous for the time being. But if the things get okay, then I will just use Luminous. But at this point, I still upload files, maybe announcement, if there are any, will be appear in both for the time being. All right. So if you can't find anything in IVLE, then go to Luminous. Okay. Just to remind you that the midterm test is likely, although it's not confirmed yet, it's likely Saturday, 9th of March in the afternoon. But it's still pending on whether we can get the venue. If no, we may have to arrange some other time. Most likely will be in the evening, during the weekdays of week 7. When I say evening, it may be 9 o'clock in the in the night, right? We try not to, but at this point, it's still not confirmed. Okay, so probability, right? In the last lecture, we discussed about conditional probability. All right. So this example 7 is a very simple example. Okay, there are two events. Okay, one is the professor is a bad morning lecture, and then B, the same professor gives a bad lecture in the afternoon. So are these two events independent? Okay, so from statistical point of view, we will not try to guess. All right, we have to know what is the probability that both events occur, so that we can work out whether they are independent or not. Or in other words, whether the conditional probability are the same with the marginal probability. Which means that we'll discuss this later in the chapter. But what I'm trying to tell you is that if this is the same, this is just one definition of independent events. So my point is, don't try to use your whatever experience to judge whether two events are independent or not. We have to use the definitions. Okay. So here we are given that, all right, we know, we don't question about how to get it, but suppose we are given these probabilities. Probably we're getting event A, event B, and intersection of the two events. By the way, don't just write down probability of A without saying what A means, event A means, all right? So somewhere you have to write down what do you by A. A is the professor gives a very bad morning lecture. Of course, you can write it. Oh, professor gives bad morning lecture and so on. You can write it like that. But the point is, if you have to use to find these probabilities to describe, or somewhere you also have to describe or write down the probability of A. So if you use the words, then that means each time you have to write down what does this event. You have to describe the whole event. But if I specify the event at the beginning, event A means this. So whenever I see A, I have to refer back, it means that the professor gives a bad morning lecture. So this means that the professor gives both morning and after lectures. They're very bad. All right? So from there, we try to calculate this probability. So what I want you to know is the relationship when you have this, all right, A complement, B complement thing, you have to be aware of that. So the first one, very straightforward. Follow from the definition, it will be the probability of A intercept B divided by probability of A, which is 0.1 over 0.3. All right, these are from the previous slide. Now the second B, the part B, probability of B complement given A. Now because they are conditioned on the same conditions, so therefore this one is just 1 minus probability of B given A. Because B prime is a complement of event B. So it's just 1 minus that. So the answer is 2/3. I always keep telling you that try another way if there is. So this is based on the knowledge that B and B prime complement. So how about I follow from the definition? So the definition of this one will be probability of A intercept B complement divided by probability of A. This one you need more work. But is it possible to get the answer probability of B intercept B A intercept B complement? And the answer is yes. From what we know, this one is equal probability of A minus probability of A intercept B. Right? It looks like a magic, but basically it just simply says that, okay, A, I divide into two parts. They are non-overlapping. And combined together, union together is equal to A. What are these two parts? One is A common to B. The other part is A common to B complement. That means A, those you find in A and B, put it one group. Those you find it in A but not in B, you put it in another group. And these two add up equal to A. So we are given probability A, we are given probability A intercept B, so we can calculate this one. So you can double check the way through this definition of conditional probability, whether you get the same answer. While the first one that I mentioned, I use the property that complement event, probability of complement event B prime given A is just 1 minus the probability of B given A. But this is not true. Probability of B given A is not equal to 1 minus probability of B given A prime. This is not true. All right? You can only work on the probability of a complement and the probability of an event and its complement. But the condition must be the same. Is this correct? Yes, this is correct. The condition basically is the sample space, all possible outcome. So you restrict to A, both are on A, then it's okay. But this one is not. This is when we're talking about A and A complement. We don't have these properties. We are not asking, we're still asking for probability of B in both cases. And one condition on A, the other condition on A complement. They are different conditions, so you cannot use this complement event properties. Okay, so that's what I want to add to this example. You can read the others. Okay, so from this definition of conditional probability, so we derive this, we call it multiplicative rule of probability. Mathematically, there's no difference. We just remember the definition of conditional probability. It is A intercept B divided by probability of B. So what we do is just multiply both sides of this definition of conditional probability so that we have probability of A intercept B equal to probability A given B times probability of B. So mathematically it's very simple. But once I write it in a multiplicative rule, then you can see that on the left-hand side, all right, it simply means that I want to find out the probability both A and B occur. Okay, I need both A and B. Now this one I can consider as the product of two probabilities. One is the chance of one of the event occur first, and then multiply to the probability of the second event given the first event has occurred. So that instead of looking A intercept B, I look it step by step. I look at it A first, what's the chance, and then look at B occurs given that A has occurred. So combine two together. So why A first? We can have B first, yes, so that there's the second identity. So this is the multiplication rule. Of course, in order this is valid, you must have probability of A or probability of B must be bigger than 0. Because otherwise you cannot multiply, because in that case the definition of conditional probability is not applied, so you cannot apply this multiplication rule. All right, so this is enable us to calculate two events will both occur. Okay, so sometimes you may confuse which one comes first. So I consider A first and then calculate B given A, or B first and then A given B. In fact, it depends on the problem. There's no unique way to identify them. So we can extend this idea to 3 events to occur. We want all these 3 events occur. So it's equal to probability of A times probability of B given A times probability of C given A intercept B, provided that probability of A intercept B greater than 0. So in general, the multiplication rule is like that. So if you want to have the event, all the n event occurs, you can consider as, first of all, calculate the probability of A1 occurs times probability of A2 given A1 times probability of A3 given A1 intercept A2, and so on. All right, so this is the general way to present the multiplication rule. But in general, usually 2 or 3 events should be complicated enough for us to identify. All right, provided that this probability is greater than 0. All right, so let's look at some examples. Now, suppose we have 12 shares. Definitely we have 12 items into 2 groups. One group, 3, they are white shares, or 3 have certain properties, and the remaining 9 does not have these properties. So we divide it into 2 groups. So in this example, I use shirts and white shirts and non-white shirts. All right. So 2 shirts are drawn random, 1 by 1 without replacement. 1 by 1 without replacement. So you can consider take 1 shirt first. All right. So what is the probability that both of the shirts are white? What's the probability there's only 1 white shirt? And if 3 shirts are chosen at random, what's the probability that all are white shirts? All right. Now there are 2 approaches, at least 2 approaches. One is to use what we just learned using the conditional probability. But you have to define what are the events that you are looking at. The other one is still go back to your previous, use the combination, number of combinations, and number of possible combinations, number of combinations that fulfill or satisfy the conditions. All right? So in other words, we can either use the probability, conditional probability of the multiplication rule, or use the counting method. Count how many ways that you can have 2 shirts that you choose, both are white. And then over the number of ways that you can choose out of these 12 shirts, any 2 shirts. Things like that. Okay, so here I define A1 is the first shirt, is a white shirt. And A2 is the second shirt, is a white shirt. All right? So we have 12 shirts, so we pick one shirt, see whether it's white shirt or not. So obviously it is 3 over 12. There are altogether 12 shirts, you just pick 1, and 3 of them are white, 9 of them are non-white. So the probability A1 is 3 over 12. How about probability of A2? Probability of A2. The second shirt is white. Now the outcome, the probability of the second shirt is white shirt is much harder to compute. Why is it harder? Because you need to know what is the outcome of the first one. So it may be easier to answer this question, A2 given A1. That means if you know that the first shirt is a white shirt, then what's the chance that you got the second shirt is a white shirt? So if the first one, after you draw the first one, 11 left, all right, and then how many are white? 2 of them are white. Similarly, I can also work on A2 given A1 prime. What does that mean? It means that if the first shirt is not a white shirt, all right, so that means you still have 3 white shirts remain left, and then you choose from them. So it is 3 over 11. As you can see, the 2 does not add up equal to 1. All right? Then, of course, from there, we may be able to work out what is the probability of A2. But at this point, what we want is A1, first shirt is white, second shirt is white. So basically, we want A1 intersect A2, which is this one times this one. So give us the answer. So the answer is 1 over 22. All right, so this one applying the conditional or multiplication rule idea. First shirt, and then after we know what is the outcome of the first shirt, then we try to get a white shirt. If I use combinatoric arguments, then basically we are choosing 2 shirts out of 12 shirts. So this is the number of ways that we can choose. Out of this one, I divide into 2 groups. Out of the 3 white shirts, I need to choose 2. And out of the remaining 9 shirts, how many do I have to choose? 0. I'll check whether this will give you the same answer. All right? So this is another approach to the problem. Which one to use? Sometimes one way may be more easier to compute. Okay, like in this case, I think the multiplication rule may be easier. All right, then how about the second one? The second one, we want both. Sorry, we want only 1 white shirt. So the first one is white shirt, and then the second one, I want it to be non-white. So it's 1 minus 2 over 11. But this only gives you one possible outcome. They have 1 white shirt. That means the first is a white shirt, the second one is a non-white shirt. But it can be, all right, it can be okay, so can be the first one is a non-white shirt, while the second one is a white shirt. So this one, how to get it? It is non-white shirt, so 9 over 12. A white shirt, 3 over 11. So it's similar to the first one. Although the numbers are the same, but the interpretation is different. This means that the first one is a non-white shirt, means A1 prime. The second, 3 over 11, is the probability of A2 given A1 prime. So multiply together, it will give me A2 intersect A1 prime. So this is how we got it. All right, so the answer is 9 over 22. All right. How about if I use combinatoric approach? So we don't care which one is first. What we need is from this 3 white shirt, we pick 1. From the 9 non-white shirt, we also pick 1. All right? So you check whether this is correct. So we want to choose 1 from the 3 white shirt, and then 1 from the... See whether this is correct. All right? In the conditional probability, in the multiplication rule, we have to know what condition. But when the combinatorics, when we choose, all right, we know how many ways can we get 1 white and 1 non-white shirt. So basically, out of this one, I divide into two groups, white shirt and non-white shirt. From the white shirt, I choose one. It doesn't matter which one you choose first. All right, so choose one from the 3 white shirt and then one from the 9 non-white shirt. All right, how about number 3? Number 3, I write it in this form. All right, so A1, the first is a white shirt. A2, I don't care about the first and the second one, so it's this is called A2. But if I write A2 given A1, then what does it mean? It means that the first one is white, the second one is white. I don't care what the third outcome is. All right, that's what it means. So basically, if I want 3 white shirts, basically it's A1 intersect A2 intersect A3. Right? So I want this one, so I break it down into first one is a white shirt, so it is 3 over 11. Second one is a white shirt. Given that the first one is a white shirt, so it's 3 over 12, right? That 12 white shirt, 12 shirts altogether. So this is 2 over 11, and then finally there are only 1 white shirt left with 10. So this is the answer of all the 3 are white shirts. So if I use the combinatoric argument, so what does it mean? I still have to, this time I have to choose 3 out of the 12 shirts. Out of this, the 3 white shirt, I have to choose all 3. 9 non-white, I have to do 0. So that's how we look at it. The combinatoric part, I just divide into 2 groups. It doesn't matter the order. All right? If you consider order, it's a little more complicated. You have to consider the number of permutations, so it's a bit more complicated. All right, example 2. Okay, I think you can read it yourself, example 2. Okay, example 3. So we have a deck of cards, 52 cards, excluding all those jokers and things. So we have 52 cards. 4 suits, 13 each, so it's 52 cards. So what's the chance that both cards are greater than 3 and less than 8? So in other words, it is 4, 5, 6, 7. Now, if you use the combinatorics argument, then basically you want to choose 2 cards out of 52 cards. Out of this one, I have to divide this. If I use combinatoric argument, I have to divide these 52 cards into 2 groups. One group satisfies the conditions. What are the conditions? 4, 5, 6, 7. The cards are either 4, 5, or 6, or 7. So the other group is the rest. All right? So divide these 2 groups. So the group satisfy these conditions. There are 16 of them. 4, 5, 6, 7. Each one has 4 cards, so it's 4. We choose 2 cards. And then the remaining 16 was remaining 39, right? We have got 16. 16. So the remaining is 52 minus 16. So it's 4 times, how many? 39? No, 36. Thank you. Yeah. 4 times 9. There are 9 remaining cards. 4 times 9. So we choose 0. All right. So that's one way to do it. Then, I always use combinatorics. And wow, yes. Sometimes it may be very hard to use the combinatoric argument. All right. This one is easy. Okay. So my solution here, use the the multiplication rule. So that I look at first card, satisfy the conditions. So it is 16 cards out of the 2 cards. So once you pick this one, the remaining 51 cards, there are only 15 that fulfill or satisfy the condition. So multiply them together. All right. So the answer is 20 over 221. Okay. Now, a deck of cards may be easy to look at it. So now we look at this problem. So we have this doctor correctly diagnose a particular illness, this must be very hard to identify. So only 70% chance identify correctly, diagnose it correctly. All right. Now, if the doctor makes an incorrect diagnosis, then the patient will enter a lawsuit with chance 90%. So in this case, we have at least two events mentioned here: correctly diagnosis and then lawsuit. All right. So, if this one I call it A, then what is A complement? Sorry, let me see what notation. Oh, I use D and U, right? Okay. So this is D, event D. So D complement means that the patient, the doctor diagnoses the disease incorrectly. Then lawsuit. All right. So this one basically means probability of D is 0.7. Probability of given that incorrect diagnosis, so it's D complement, enter a lawsuit is 0.9. All right. So what is the chance that the doctor makes an incorrect diagnosis and patient sues? So this is very straightforward. What we are asked is to make an incorrect diagnosis at the same time and the patient sues. So just multiply the two and then you will get this answer. Oh, sorry, not multiply these two, but you have to work out from here what is the probability of D prime. So it's 0.3. 0.3. So it's multiply this with this. That will give you this. Okay. Now this is a little example 5 that's a bit complicated. So we have 4 individuals. Okay. They go for donation and they don't know their blood type. Okay. Now this is very important. Only 1 out of 4 actually has this blood type O+, let's say. Or A+, sorry, A+. All right. So the others have non-A+ type. So we select one at random. So what's the chance that at least 3 individuals must be typed to obtain the first desired type? And the third donor's blood type is the correct one. Now this one have an implicit implication because there are only 1 out of 4 are having this blood type. So in other words, in order the third one to be the correct one, that means the first donor, the second donor, they are not of A+ type. This is understood in this problem. All right? In general, we don't know what happened to the first one, what happened to the second. You have to work out. But in this particular case, the first one must be non-A+. The second donor must be the second donor must be non-A+. So that the third one is A+. A chance of having an A+. Okay, so now I define A to be the first donor, not A+. B, the second donor, not A+. So the probability of A, therefore, only 1 has A+, so non-A+ is 3/4. Well, if we know that the first one is non-A+, what's the chance that the second one is a non-A+? So there are 3 left, and 2 of them are non-A+. Only 1 out of the 3 remaining are A+. So non-A+ is 2/3. So at least 2 individuals are type, and the first 2 donors are non-A+. All right? So this is what I said. The first 2 must be non-A+ in order to get the third or the fourth one being A+. So at least 3 individuals are type is equivalent to the first 2 are non-A+. So because if the first 2 are non-A+, then the A plus must occur at the third donor or the fourth donor. That fulfill the at least 3. You can have 4, being 4 individuals or 3 individuals being typed at least 3. So it's equivalent to probability A times probability of B intersect A. Or basically you need the first 2 to be not A plus. Then the third or the fourth must be A plus. So the answer is 1/2. All right? 3/4, which is this probability. This is probability of B given A. So the answer is 1/2. So what's the chance that you can identify the A plus in the first 2 donors? What's the probability that you get the A plus in the first 2 donors? So, oh, sorry, this is the 1/2. So the answer is 1 minus 1/2. What I mean is that you can get at least 3 individuals are typed, or you need only 2, 1 or 2 to get. So it's complement of each other. But it turns out this is half, so the answer is the same. It's 1 minus 1/2. Okay, third donor is A plus. So it's different from the previous one. The previous one need at least 3 or 4. Here you explicitly want to get the third donor is the correct one, get the A plus. All right? So you have to do, this is the first 2 non-A plus. Then now you left with 2 individuals, and then one of them must be A plus. So the probability is half. All right, so the answer is one quarter. All right? Now, so I have a question. So this turns out to be 1/4. So what is the probability? The first one is A plus. What's the probability? First one is A plus. 1/4, 1/4. Same as this number there. So then naturally I will ask, what is the probability that identify the second donor is an A plus? What is that chance? And if you work out, it's 1/4. Then what's the chance that the fourth donor is A plus? Also 1/4. What does it mean? It means that it doesn't matter which one. I mean, the chance of first, second, third, or fourth being A plus, out of this scenario, they are the same, 1/4 each. All right? I don't know whether you heard about this one. If you have a bunch of keys to open a door, so you can try. So it doesn't matter whether you try the first one or second. I mean, okay. So you take one key, try it out, not correct. Then, of course, you take another one. So in fact, the chance of you open the door, all right, in the first trial, use the first key, or the chance that you open the door using the second key, that means you fail in the first one and then get open in the second one. In fact, it's all equal. So it doesn't matter which key you use first. All right, they're the same. So in other words, if you draw a lock, I have a box with the first prize in the box, the tickets, then you take. You don't have to fight. You don't have to fight to take. I'm the first one who take the card. All right? I can wait until the last one. It's the same chance. All right? Same chance. Okay. So we move on to a law of total probability. This is, idea is very simple. All right? But when you use it, you have to know, you have to understand this law. So it's very simple. It's basically saying that, okay, I divide this sample space, all possible outcomes, into n parts. So these parts are non-overlapping, and then if we put them together, it will be the sample space. So that means I try to, we call this a partition. Mathematically, it seems that it's saying that, okay, mathematically, this is what we mean. All right? So in other words, you have S, you partition an A and A complement. So this one is a partition. A and A complement, no overlap, no intersection. And the union is the S. All right? In probability terms, so you must know this word, mutually exclusive. This is the term to use to describe AI intersect AJ equal to empty set. That means any two of them or any three of them, there are no intersection, no common points. They are non-overlapping. So we call this mutually exclusive. Exhaustive, mutually exhaustive exhaustive means that you put all this together, you will cover all the aspects. In other words, any outcome in the sample space must belong to one of those AI. So that's what we call exhaustive. You cannot find any one outcome which does not belong to any of these AIs. Then we call these AIs as exhaustive events. Then for any event B, wow, it looks, okay. Mathematically, we write it like that. It basically saying that, okay, B, I also divide it into n parts. So one part is B common to A1. One part is B common to A2. And just put all this together. So that will be my B. All right? So probability of B is equal to the sum of the probability of B intersect AI for all the i's. And by the multiplication rule, probability of B intersect AI is equal to this. All right? Okay. So here's the picture. A1, A2, oh, it's supposed to cut over here. All right, so we divide it into AN parts, non-overlapping. And then this is B. So probability of B is equal to probability of A1 intercept B, this part. Oh, cannot see the color. In color. Okay, so this is the part B intersect A1. So this is the part B intersect A2 and so on. So basically, we just look at the B and look at the part that B common to AIs and then add them together. All right, so this is how we have these total probabilities. In fact, we have been using this one before. Remember the one that okay, you remember this one? Probability. Probability of B equal to probability of B intersect A plus probability of B intersect A complement. So we have been using it. This is the one of the example. This is the simplest one. So a set you can partition into two parts, A and A complement. All right, so this is a simple application of the law of total probability. Okay, so now let's look at this example. We have 3 machines. All right, so each machine has different proportion of defective screws produced. And these 3 machines, okay, combined give us the total production. So make sure that these 3, event A, B, C, from machine A, from machine B, and machine C, combined together is the total, is all the screws that we produce. So make sure that these 3 numbers corresponding to these 3 events add up to 1. If they are not adding to 1, then that means these 3 events are not exhaustive events. There may be another way to get the screw. Either machine D or the company just buy from someone else. All right? So make sure that these 3 numbers, 3 probability, this represents the probability that add up to 1. So you can consider probability of A equal to 0.35 and so on. So this means that probability of a defective items, defective screw, given is from machine A is 0.02. All right? Okay, so if we select one screw, randomly, what's the chance that it's defective? What is the probability that it is defective? So it depends on whether it comes from machine A or machine B or machine C. So what is the probability that it's produced by machine C given that it's defective? So we want to compute this probability. Defective and it's from machine C. All right, so to get the, okay, you can think of it, although it helps, but don't rely too much on it. Sometimes the situation is so complicated, you can use this tree diagram to represent it. So this one you can consider, you start, there are three possible machines, all right? This is, what are this probability? Okay, 0.35, 0.25, and 0.4. We start from a node, branch out. There are three branches represent machine A, B, and C. And each branch has a probability associated to it. So that means 0.35 to get to from machine A. Then from machine A, I branch out two. What are these two branches? What are these two nodes? Defective and non-defective. Make sure that all the branches come out from the node. They are mutually exclusive and exhaustive. So in this case, it represents the screw, whether it's defective or non-defective, coming from a machine. And what's this probability? This is 0.02. So what is this one? This one will be, now coming out from the same branch, same node, the probability must be add up to 1. So this three add up to 1. This three add up to 1. So this also add up to 1. So it has to be 0.98. Then D and D prime. D and D prime. So this one is 0.01, 0.99, 0.03, and 0.97. All right? Then you ask what is the probability of B, probably a defective item. So you have to add up this probability, which is A intercept D, and this one is B intercept D, and this one is C intercept D. All right? How to get the probability? Multiply the two probability that you go from the root node up to the D. So this part, this one, is probability of this. This is the probability of B intercept D, and this is the probability of C intercept D. So the chance getting a defective screw is 0.215. 0.215. 0.0215. Now, if we know that we have a defective screw, what's the chance that it's from machine C? So follow from the definition, conditional probability of C given D is probability of C intercept D divided by probability of D. So is equal to 0.5581. So what does that mean? Now you can think of it. If I just randomly select a screw, what is the chance that it is from machine C, produced by machine C? So it's 0.4, right? I don't know what screw it is. I just take one screw. What's the chance that it's from machine C? It is only 0.4 chance that it's from machine C. But now if I tell you that, okay, this screw is defective. So what's the chance it is from machine C? And now the chance changed to 0.5581. 56%. Instead of 40%, now it becomes 56%. Why? Because you can see that, all right, among the three machines, the proportion of defective is higher for machine C. It's 0.03. So of course, it's likely that if it's a defective machine, it is from machine C. All right. So in other words, this piece of information, given that this is defective screw, it is more likely from the machine C. If without this information, okay, what's the chance that the screw is from machine C? The chance is 0.4, 40%. All right. Okay. Now this one, we have two bats, and they have different number of white ball and black balls. In fact, even they have the same, but you still have to look in carefully. So now we take one ball from a bat, first bat, okay, this one. This is the first one, all right? And then put it, don't see what ball you take, and then put it in the second bat. Now, what is the chance that the ball now drawn from the second bat is a black ball? Okay? Now, because in the process, the outcome or the number of number of black balls in the second bat depends on what ball you draw from the first bat. So you have to consider this, all right, carefully. Oh. So now I let A1, the ball drawn from the first bat is a white ball, and A2 is the first ball drawn is a black ball. But because in the bat there are only two types of balls, white and black. So A2 basically is A1 complement. All right? Because there are only two types, white and black. So B is the ball taken from the second bat, is a black ball. All right, so probability of A1 is 4/7. Because there are 4 white ball, so probability of A2 is 3/7. You can forget about this one. There are 3 white balls. 3 black balls out of 7 in the first bat. Okay. Now, if it's a white ball drawn from the first bat, then, okay, condition of A1, then the chance of getting a black ball, because they now have 5, because the first one is you take a black ball out of the first bat and then put it in the second bat. All right. Oh, okay. Okay, I'm a little bit confused. So what's the question, a white or black ball that we want to find out? It's a bit, okay, so here, okay, ask about the second bat drawn is a black ball. But in here, okay, in fact, it's the same thing. Okay, but this one is the chance of getting a white ball. All right, at first the second bat has only 4 white ball. But if the first one is a white ball, you put it, so now we have 5 white ball. So the chance is 5/9. All right, so similarly, you can work out if the first ball is a black ball, then what's the chance that you get a white ball? So apply the total probability, you get the probability of B. So there's some mistakes here. So you correct it yourself. All right. The white and black, the two words seems confused. I mean, mixed up. So the question is, try to fix it as simple as possible. All right. Okay. This one is just a little bit more complicated. So we drive along a road, and there are 4 locations with speed camera. All right. So this one is just assume that it operates 40%, 30%, 20%, 30% of time. I don't know in real life. Don't rely on that. Assume 100%. Otherwise, you may get speeding tickets. So here we assume that the speeding camera operates some of the time randomly. You don't know. So when you're speeding, there are only 40% chance that you're being caught. All right. Of course, if you're not speeding, then 100% that you will not be caught. All right. So this guy may speed, okay, with these probabilities. All right. We have also these 4 probabilities. So these four probabilities do not add up to 1. Why? Okay, unless we have a system that we only have one speed camera works among these four at any time. All right? It's supposed to be independent. So this four percentage should not add up to 1. You don't expect it to add up to 1. All right? Okay. So we want to find out what is the probability that he received a speeding ticket. So AI is the event that he passed a certain location. So this add up to 1, right? Why? Okay, it's basically saying that he is driving through this expressway, and we assume that there are 4 different ways to pass through. They are not sequential. If they're sequential, then it doesn't, it shouldn't add to 1. So in other words, I can choose to pass this from A to B, or if I want to drive from University to Orchard Road. So I have many routes to go through, all right? But then, okay, so there are different locations that have this speeding camera. So I just have choose one route, and there's only one speeding camera. All right. So if I choose, okay, so I may choose L1 through L1. So I will pass that with probability 0.2. All right. So that's why we have to add up all this A1, A2, A3, passing through A1. And when you pass it, you're speeding. All right, so that means the first term means you pass through location L1 and speeding. And similarly, pass through location 2 and then speeding. All right, so altogether, so you work out what's the chance that speeding? 0.27. 0.27. So if you are caught speeding, what's the chance that you use location 2? Use the location 2. So the probability follow from the conditional probability, all right, is 1/9. All right. Now, so in other words, originally the chance of getting through A2 is 0.1. All right. But if it is got speeding, then the chance that it got A2 is slightly increased to 1/9. Slightly increased to 1/9. Another example to use this total probability. Okay, so we have one 50-cent coin, one 20-cent coin, and one 10-cent coin. 3 coins. We pick one at random and toss it 4 times. The 10-cent coin is fake with 2 heads. Right? So, if that means this is the condition on the event that you have 4 heads. So in other words, now I have 3 possible outcomes. One is a 50-cent coin, all right? The other is 20 cents and 10 cents. What do I use? A, B, C, okay. The other way wrong. All right, so these are the events. And I have only these 3 events. So the union of all this will be the sample space. Not the sample, but all possible coins that I can choose. And then another event is 4 heads. I don't care about the others. The others I just can call it non-4 heads, including any possible outcomes which is different from 4 heads. So now, if the 10 cents is chosen, the probability head is 1. All right. So now, remember, although I write it probably head, if this coin is chosen. So in other words, the probability of getting 4 head, given that it is 10 cents coin. This is equal to 1. Right? So no matter how you toast how many times, it's always head. So 4 heads out of 4 toasters with probability 1. While the probability of 4 head, given that it is a 20 cents coin. So this one, it is 1 over 1/2 times 1/2 times 1/2 4 times. So it is 1 over 16. Similarly, probability of 4 head, given that it is C, it is also 1 over 16. All right? So this is what we have. So, if we choose a coin randomly, each one should be 1/3 chance. So, applying the law of total probability, getting 4 head is equal to from A. Given A, you got 4 heads. B, and given B, you got 4 heads. And given C, you got 4 heads. So you multiply them. So the chance of getting 4 heads is 3/8. It's not 1, but the chance is much increased from 1 over 16 to 3 over head because there's one coin that have 2 heads there. So now, given 4 heads, what's the chance that I got A? So it is A intercept 4 head probability divided by probability of 4 head. So what it says is like this. You have a 10 cents coin, 20 cents coin, and 50 cents coin. The probability are equal, so 1/3 each. This one, you got 4 heads and non-4 heads. 4 heads and non-4 heads. 4 heads and non-4 heads. All right, so the probability is 1, 0, 1 over 16, 15 over 16, 1 over 16, and 15 over 16. So probability of getting 4 head can be this one. You get 4 head through this path, through this path. Getting 4 head through this path. Getting 4 head through this path. And you have to add up all the probability of these 3 paths. So you got probability of 4 head. Now, knowing that we have 4 heads, so it's either from this path, or from this path, or from this path. So now the question is, what's the chance that it is from the first path, from the 10 cents coin? So we look at this path, probability, and then over the probability you get 4 heads. So the answer is 8 over 9. So in other words, if you know that there are 3 coins and you know that one of them is fake, all right, so you select one. So what is the chance that you get a 10 cents coin? Without the information of the how many toss, how many heads there, the chance is 1/3. But now I select this coin and then I throw it 4 times. And then I got 4 heads. So the probability of that being a fake coin with 2 heads is increased to 8 over 9 instead of 1/3. Now it's 8 over 9 because of this information. Now if the outcome, you toss 4 times, you got 3 head and one tail. Then what is the chance that you will get a 10 cents coin? The fake 10 cents coin. So it's 0. All right, it's 0. You can work it out. So it's 0. All right? So, okay. Bayes' theorem. Fancy name now. But, okay, we have to credit to this gentleman. He first mentioned about this. But basically, it's just what we have discussed. Bayes' theorem. What is Bayes' theorem? So we have this A1 to AN partition of S. And it's simply saying that if we know something happens, okay, you can think of it like this. So we have A1, AK. And they each have B or B complement. All right? So, now, if we know B has happened, so what is the chance that AK happens? That's the idea of Bayes' theorem. It looks very complicated, this part. But if you think of it, what does this mean? This comes from the law of total probability. What does this represent? This basically represents the chance of getting a B. You're saying that, okay, what happens, the chance get AI, and then the chance of even AI has occurred, what's the chance got a B? Then you combine all these parts together, and that is the probability of getting a B. All right? So Bayes' theorem is nothing fantastic. It's just like this. It's just a conditional probability. But the interpretation is like this. All right? So it's sort of like a two-stage. All right? Like this sequence. First of all, we got AI occur first, and then followed by B or B complement. Or more, maybe more than that. But then, okay, so now in the second stage, we know something about the second stage. So now we go back to check what happened to the first stage. What is the chance of getting a certain event in the first stage? All right, here's an example. So a newly constructed house collapse. All right, whether the design has fault or not, right? Anything can happen. So when you have a house, there's a chance that it will collapse. But of course, the chance of, okay, if it's a faulty design, then the chance of collapse may be higher. All right, here we try to use some figures, may not be very practical. Okay, the chance of design is faulty is 1%. So the design is okay, it's 99%. Okay, if the design is faulty, wow, it still can survive. Huh? So only for the collapse chance is 75%. Otherwise, if the design is okay, the only 0.01% will collapse. All right? So what does it mean? It means that we have all this. So now, okay, usually you have this sequence. First of all, you have to design the house and then build the house. Collapse will only when you have the house, then you will have this event, collapse or not collapse. So collapse is in the later stage. So now, we see the outcome in the later stage, the house collapse. So you ask yourself, what is the chance that the design is faulty? Yeah, it's a faulty. All right? So it's like this. If I would like to draw the tree diagram. So these faulty design or non-faulty design. All right? And then collapse or do not collapse. Oh, C and C complement. So now we see collapse, but we don't know which path they gone. So we want to figure out that. All right, so B is the design is faulty, A, the house collapse. So we are asked, we are given that probability of a faulty design is 1%. So probability of A given B is 0.75. We also given that if the design is okay, the chance of collapse is 0.001. Okay, you can see that these two do not add up to 1 because they are different things. All right, the complement is on the condition, not on the event itself. Okay, so apply the total probability, the chance of collapse. All right. Yeah, there's a typo here, right? Obviously, B occur, this should be B complement. So put back a complement. Okay, so this is the probability of B complement, and this is the probability of A given B complement. So after all, we don't care whether the design is faulty or not. A house with a probability of 0.0076 of collapse. All right, the collapse may be due to faulty design or just due to it collapse. Even if the design is okay. So now, we know that it has collapsed, and what's the chance that the design is faulty? So we apply this Bayes' theorem, or conditional probability, because we have already worked out probability of A, which is 0.0075. So the answer is 0.987. 0.97. So what does it mean? It means that if we see a house collapse, okay, if you choose randomly a house, so it's likely that it is from a faulty design. What's the percentage? 1%, right? 1%. 1% that it is, the design is faulty. But now if we know that the house collapsed, so now we know that it most likely this house has a faulty design with a probability equal to 0.98, 0.98 or 0.99 almost. All right? So the Bayes theorem basically is just application of the conditional probability as well as the total probability. The idea is that if you know something about at a later stage has happened, so you try to work out backward what happened to the probability of the first stage, the events in the first stage. So here's another example. So, okay, insurance company believes people can divide into two classes. Two and only two classes. So it covers accident-prone and those who are not. This is a very simple way to classify or to get two events which are mutually exclusive and exhaustive. One has this property, while the other group does not have this property. So in this case, one accident-prone and the other is no. All right? So accident-prone with accident probability equal 0.04. All right? While for non-accident-prone, the probability is 0.02. If 0.04 change to 0.02, what does it mean? Why we bother to separate the two groups? They have the same probability. So these two groups have different probabilities. All right? Of course, you don't expect this one to be smaller than 0.02, right? Otherwise, you don't call it accident-prone. So accident-prone means that the chance of getting accident for this group of people should be higher. So in this example, we use the figure 0.04. All right. This is important. Now what we are saying, okay, let me see what my events are. B accidents, A1 accident-prone, A2. Okay. Okay. So what we are saying that, okay, let this one, I use A1 and this one A2. But A1 and A2 are complement of each other. So what we have here is the probability of having accident given is A1 is 0.04. All right. Now, getting a habit, try to identify the events. Okay? And also see the link. So now I use A1, A2. So, but you also have to see that A1 and A2 basically is complement of each other. A1 is a complement of A2, or A2 is a complement of A1. All right? So then try to link up all this given probability. All right? Whether it's a probability or a conditional probability. So in this case, we're talking about accident-prone persons. All right? So it is, if it's given the condition, it is an accident-prone person, then the chance of having accident is 0.04. So similarly, the probability of B given A2 or A1 complement is 0.02. But we still need to know what is the probability of A1 and what is probability of A2. So here I say that probability A1 is 0.3, 30%. So with all this, we can answer the question, what's the probability that a new policy holder will have an accident within a year of purchasing the policy? In other words, we are asking this probability. No condition. What is the chance that this new policy holder has an accident in the coming year? What we know is that if it is from A1 group, the chance is 0.04. If it is from A2 group or A1 complement, it is 0.02. But what is this? Now, without knowing what is the probability of A1 and probability of A2, Without this, if you don't know this one, you cannot proceed. But we are told that 30% of them are A1. All right? So the next question is probability of B having an accident. What is the chance that he belongs to A1? All right? So I think you can work it out yourself. So I skip. All right? So the answer is 6/13. If you see that there's accident, so it belongs to accident prompt, instead of 30% now increase almost to 0.5. Almost to 0.5. So you see someone, if you select one individual, only 30% chance that he is accident prompt. But now I know that accident has occurred for this guy, then therefore this guy, okay, belongs to the accident prompt group. The probability increased to 6/13. Okay, so this is just another example. We have 3 identical cards. Identical in this means that the physical size, but the color is different. Okay, one card got both sides are red, one is both sides are black, and another card is red and blue. Sorry, red and black. One side red, one side black. All right. So mix in the box, so you don't see the color, you don't see them. You draw one card, okay, put on the table, so you can see at least one face. All right. So if the upper side is red, so what is the chance that the other side is black? All right. Okay. So what are the 2 stages? So you can think of it, in this whole process, the first stage is to select a card. Select a card. Out of these 3 cards, there are only 3 cards that we consider. So 3 cards. And then the second one is the color of the other side of the card. That means the one that showed you, all right, we know. But then what happened to the second? The color is being black on the other side. So we let AI be the event that the I card is being selected. So then B is the upper side of the color is red. What we are asked? Yeah, if the upper side is red, then what is the other side? Is black. Okay, so because these 3 cards are the same size, okay, so it's randomly selected, so it's 1/3 for any one of the cards being selected. And if it is A1, okay, A1, both sides are red. The first card, both sides are red. Second card, both sides are black. So red, black. So black, because the cards are both red. Okay, the cards are red, so both sides are red, so the probability is 1. Second card, both sides are black, so the chance is 0. So the third card is 1 white and 1 black. So the chance that the card with the upper face being red is 1/2. So given that B has occurred, so given that the upper side is red, so what is the chance that it is from the third card? Now if the upper side is a red card, then we're sure that it cannot be the card with both sides are black. All right? But what we ask is, okay, if the top card is red color, what's the chance that the third card all right, you have a third card. I mean, the A3 happens. This is the same as, what does that mean? B means that the upper face is red, all right? So we are asked, what's the chance that if you see the upper face is red, what is the chance that the bottom one is black? Which is the same as saying that A3 is being chosen. All right? This one you have to know what we're trying to do. I identify events, which card? So A1, A2, A3. A1's both red. A2 both black. A3 one white, one red, one black. All right? Then now I draw a card, and then the upper face is red color. And ask what's the chance that the bottom, the other face is black, which is the same as asking what's the chance that you draw the third card. So it's probability of A3 given B is the probability that we want to find out. All right? So in this exercise, I try to identify the events, which card to choose, and the upper face of the card is a red color. These two events. I mean, these groups of events. I did not specify what is the chance that the other side is black. But by getting this probability is equivalent to say that, okay, now I know the upper face is red color. What is the chance that you get the bottom, the other face is black? Because this is equivalent to A3. So we work out all this, and the chance is 1/3. 1/3. So it's strange, huh? What is strange? Think of it. What is the probability of A3, huh? One-third also, right? I did not tell you what is the outcome. I just take one card. What is the chance that you got the card with red and black? 1/3. So now I take the card and leave it on the table and tell you that the face is red. So what is the chance that it is one red, one black? So it's also 1/3. All right? So what does it mean? It means that whether you see the outcome or not, it doesn't matter. The chance of getting, okay, the one side black, all right, is the same. Oh. Okay. These two are the same. All right. But one is that you take this card. You see, the problem is that I make two events equivalent. One is the card is a red and black card. It's equivalent to when you see the red here, the bottom is a black card. Because out of these three cards, only one card, A3, happens, then you have one red and one black. So these two events are the same. Are equivalent, what I mean is equivalent. The probabilities, okay. This is equivalent to my questions there. All right, you see red, and then what is the chance that the other side is blue? The bottom is blue, is black. The top is red. So this event is equivalent to A3 being drawn. But these two probabilities mathematically work out to be the same. Okay. Example 4. This is an interesting example because it tells you that, okay, let me say the conclusion first. Okay, we want to go for certain disease and go for a test. So if test for positive, what is the chance that you have that disease? So sometimes people will think, that, I test positive, so it's the end of the world. But it depends on what we call the occurrence rate. Okay, in this case, we consider this is rare, 1/1000. In fact, this is not rare. But we consider the chance of getting a disease, of this particular disease, is 1 over 1,000. So we develop a diagnostic test, and now read the question carefully. What is this 99%? Okay, it means that if this particular guy, this person, have the disease, then the chance of positive result is 99%. Good, huh? So only 1% that you cannot detect. All right? But the test can be positive, can be negative. So apply to those who have disease, 99% that they identify as gives you a positive result. All right? So even better if 100%. That means if you have the disease, then you can identify that. Then that test is good. Isn't it? If we have a disease and we have a test kit, all right, then if the chance of, if the person, all right, has a disease, then this test kit will 100% identify, give you a positive result. Is it good or not? Good, huh? You have disease, then identify. But then if this test kit for apply to normal persons, ideally 0% positive results, but there's no such thing. Okay, so okay, let me put it this way. All right. So if a guy has have a certain disease, I ask him to drink water. After he drink the water, then I say that, oh, you have the disease. 100% correct, right? But for normal persons, I drink it, you don't know that, I drink it, I also say it's positive. So you have to look at what's the chance that you identify those who do not have the disease and identify positive. So here I say that for normal person, there's 2% chance that it gives you positive results. 2% chance. This is not good. So we want this to be 0, but in practice we don't have such thing. So we are saying that probability having the disease is 0.001. Probability that it tests positive, you have a disease, is 0.99. So it's good. Probability of positive for no disease is 0.02. All right, so these are the given information. Ideally, we want this to be 100 as big as possible, this one as small as possible for good test kits. All right, but apart from that, let's look at it. If an individual tests and the result is positive, what is the chance that this individual got a disease? Now, if no test results, the chance that individual got the disease is 0.001. So what is this? After the test is positive. So this is how we got it. And the answer is 0.0472. Why? You test is positive, but the chance that I got the disease is only about 5% chance. Why? What happened? Because there are 999, or because 1 out of 1,000. So there are a large proportion, 99.9% of the normal people will get positive results. So you may be one of those normal people and happens to get the positive results. All right? So that's why the probability increase from 0.001 increase to 0.047. All right? You can see that. All right? Disease, no disease. This is 0.001. This is 0.999. Positive, negative, positive, negative. Positive result 0.99, 0.01, 0.02, and 0.98 get a negative result. So for positive results, it can be through this path or through this path. Through the first path, this is the probability. Through the second path, this is the probability. So the chance of getting your positive result through the first path is only about 5% chance. So that's what I mean. A lot of positive result is from this path, No disease, and the test results show that you are, all right, you are positive. So you have to be aware of that. So this is what I just mentioned, all right. So you can check it yourself. Okay, so I stop here since some of you are already leaving, right? Okay, so we stop here. So remember, tutorial start this week, and the midterm test 3rd of March, Saturday. And next Monday is for those Chinese, right? This next Monday is Chinese New Year Eve. Reunion dinner, right? For Chinese. I think officially no class after 2 o'clock, right? Am I right? Oh, you don't know that? Okay, I may upload a webcast from last semester. Okay, cover similar topics, not exactly. Why I have to do that? Because I have the two groups. They will have class, and I missed this one. And Tuesday is a new Chinese New Year. So in other words, next week we don't meet. All right. So to compensate it, I will try to see a way to do it. So I will maybe prepare a webcast similar to the missing class, cover similar topics.